Hello everyone. In this lecture, we want to finally finish the architecture of Groth16. All of our discussion in previous lectures are needed to understand this lecture. And if you got the previous lecture and this one, you will finally understand the whole process and the architecture back of Groth16. Okay, so to start this concept, we need to overview another preliminary knowledge, and that is interpolation. What is interpolation? Interpolation is a technique that allows you to construct a polynomial when you have a set of points uh, for such a polynomial. For instance, suppose that you have a set of like x1, x1, y1, x2, y2, and blah, blah, x and yn. Now we want to construct a polynomial like f of x in a way that the f of x1 equals to y1, f of x2 equals to y2, and in general, f of xi equals to yi. Okay, so there are various algorithms to construct such a polynomial, and for this lecture, we want to overview Lagrange interpolation. So Lagrange interpolation asks us to first compute some original polynomials like L sub I, which is multiplication of some division. And then after generating multiple L sub I, you can construct f of x using the construct multiple L sub I polynomials. Okay, now we want to see how this algorithm work using an example. So suppose that we have four set of points. So f1 equals to 1. So this is like we write, we have this set, 1 and 1, right? F of 2 equals to 1. So this is like we write 2 and 1. F3 equals to 0. So this means we have the points 3 and 0. And now F4 equals to 0, which means we have points 4 and 0, right? So this means that if you have these points like this one, so the first one is 1 and 1, right? So this is the first point. The second point equals to 2 and 1, so this one. The third point equals to 3 and 0, and the 4 point equals to 4 and 0, right? Now we want to have a polynomial that is passing through this four lines. So maybe the polynomial is this one, right? Okay, or maybe the polynomial is something like this, right? Or a polynomial is something like this, who knows, right? So we want to see which of these polynomials are accessible using Lagrange interpolation. Okay, first we need to compute uh, L sub I polynomials, and the first one is L1. Okay, so L1 equals to x minus x2 over x2 minus x1. So this is x1, this is x2, this is x3, and this is x4, right? So by replacing these values in the formula, we see that uh, the formula of uh, the formula would be this one, right? 1 over 6 x to the power of 3 minus 3 over 2x2 plus 13 over 3 x minus 4. Okay. If you follow this process and use this formula and extend this formula for L2, L3, and L4, you will see that we have these polynomials. So if you want, you can rehearse and compute these three polynomials to ensure that the results are correct. So after computing polynomials f sub I, now we can use this formula and compute the polynomial f of x. So the polynomial f of x equals to y1 L1, right? Using this formula, y1 L1. So this is y1, this is y2, y3, and y4, right? So by extending this formula and then compute this computation, you will reach this formula as the final polynomial that is passing through these four lines. Okay, so let's see in our website how this polynomial is shown and how we can check by other polynomials and options. So Lagrange interpolation. So this is on the Groth16 tab. So here we have 4 points, 4 set of points, right? So we set this into 4. So the first point was 0 and 1. The second point was 0 and 1. The third point was, the second point was, let me see. Yeah, the first point equals to 1 and 1. Okay. So the first one is 1 and 1. And then the second one, 2 and 1, 3 and 0, 4 and 0, right? So this is the polynomial that is passing through the 4 points. And the formula here is similar to the formula in here, right? Okay, so now if you want to ensure that your computation is correct, you can compute f of 1 to ensure that the f of 1 equals to 1, right? This is our expectation because we already uh, assume that f of 1 equals to 1. And if you compute f of 1 by replacing x by 1, you should reach to 1. F of 2 also should be 1 because in our assumption, we assume that. And f of 3 and f of 4 also, they should be 0. Okay, so when you have the polynomial, so then you can compute the evaluation for other values of x that they are not given in the assumption, right? For instance, if you want to compute f of 5, you can replace x by 5, and you see that f of 5 equals to 3 in this polynomial. Okay, so after I got the idea of Lagrange interpolation, we want to overview Groth16. Okay, we will start with a scenario. Like in previous lecture that we overview a scenario that's they're very puzzle, that a prover needs to have 4 polynomials to satisfy an equation. In this lecture also, we want to start with a scenario. Suppose that there is a competition that some companies are applying for a project, for a counselor. So this could be a civil project or something like that. Okay, and all of the application would be evaluated by 3 referees. So the first referee is a budget referee, the second one is a risk referee, the third one is a ROI referee. They evaluate the application and then grade the application based on the quality of the application, right? So here we see that the first referee consider grade 1 for the application of the first company, right? So the risk referee considered 2 for the application of the first company, and the ROI referee considered 2 for the application of the first company, right? So these values are for the second company, right? So the 3, 4, 5, and 6. So these values are for the company number 6, right? So it should be 6 here. So there are 6 companies that apply for the project, and 3 referee are grading the application. Okay, then the referee, yeah, uh, by the way, the grade would be between 0 and 3. We assume that the referee considers 0 for application that is very bad and 3 for application that is very good. Okay, so the scenario then says that the referees should share the grade with auction man or auctioneer or something like that, and then the auctioneer compute the final grade of an application using this formula, right? So mm, the formula says that the grade of budget should be squared, and then the grade of budget should be multiplied by grade of risk. Grade of budget should be multiplied by the squared grade of risk, and then grade of risk should be multiplied by grade of ROI, and then add all of these multiplications to each other, and then add with a value of 3 to compute the final grade of the application, right? So we can consider this as a circuit that computes the final grade of the companies. So for instance, for the first company, the prover, okay, so let me rehearse, let me erase these values. Yeah, for the first company, for instance, the prover or the auctioneer entered the value 1 for the budget, and 2 for the risk, and 2 for ROI, and then by following this circuit and compute these values, so 1 multiplied by 1 equals to 1, and then 2 multiplied by 1 equals to 2, and then 2 multiplied by 1 and multiplied by 2 equals to 4, and then 2 multiplied by 2 equals to 4. So then 4 plus 4 plus 2 plus 2 plus 3 equals to 14, and this is the grade for the first company, right? So if you follow this circuit or formula for other companies, you will see that the grade for the company number 2 equals to 21, for the third company equals to 34, and for other companies we have the values. Okay, which company would be the winner? The company number 3 would be the winner company, right? Okay. Now uh, there is a concern here. So the concern here is that the prover or the auctioneer doesn't want to share the original grade by the referees to the company. Why? Because it might be because of privacy of the referees, or maybe because that they don't want to uh, allows the companies to know the referees more and understand which referee is more picky, which one is not, and then try to bribe the referees in next application, right? So here the assumption says that uh, the grade, the original grade by the um, by the referees should not be shared by public. However, the final grade plus a proof should be shared by the public, and then later everyone should be able to ensure that the final computation is correct. Okay, for instance, for the first company, when 14 and a proof is shared by public, everyone from public could understand that, okay, the prover has some values. Those values, which are 1, 2, and 2, are hidden from the public. However, the public can, can say that, okay, there were some values known by the prover that follow the circuit to generate the final grade 14. And this proof allow me as a public verifier to ensure that the computation was actually followed the circuit, right? So then the public verifier would be convinced that the final grade are computed correctly without knowing the original grade uh, assigned by the referees, right? So here, in this scenario, there are some security concerns. For instance, somebody may say that, okay, what if the auctioneer changed the values, the grade received from the referees, right? So this is a valid concern, but we assume that the um, the auctioneer is trustworthy for the referees, and the referees are ensured that those grades would not be changed by the auctioneer. Okay, so now we are seeking a scenario that the auctioneer could convince the public that he has the uh, original value or entered value for the secret, that the final outputs could be verified. So this is kind of a zero knowledge scenario, right? So we can consider the auctioneer as a prover, and now the auctioneer wants to convince the verifier that I know the input of the secret circuit. When you can convince the output of the circuit, which is the final grade, is computed correctly based on the circuit, right? So this is a zero knowledge proof scenario. Okay, we want to discuss how Groth16 allows to manage such a scenario. So the challenger actually defined this puzzle. So challenger described the scenario. So now we want to use a zero knowledge system, especially Groth16, to see how the puzzle could be given into Groth16, and then a proof is generated and finally verified by the public verifiers. So the general algorithm of Groth16 says that first you need to convert the puzzle into a valid circuit based on the constraint system. So this design system, so this one is a circuit that it is valid in mathematicians. So, but in Groth16, this is not a valid circuit. We need to design it in another form. We will discuss later. So then you need to convert the circuit or constraint system into matrix. The next step asks you to convert the matrix into polynomial. How we can convert the matrix into polynomial? We use Lagrange interpolation that we discussed uh, early in this lecture. So then finally reach to polynomials that you may ask, you may guess that we will use the knowledge from previous lecture to handle it. In previous lecture, we we had challenge with polynomials and then prove something in polynomials, equality test, pairing, and those discussion. And that knowledge from previous lecture allows us to generate a proof about knowing knowledge related to some polynomials. Okay, after the proof is generated, so verifiers could verify. Okay, now we want to follow the Groth16 system and then handle this scenario. So the first step is defining the puzzle. We already defined the scenario. So the scenario says that there is a circuit or formula that compute the final grade of the companies, and approver or auctioneer wants to convince public that the final grade are computed following the circuit without sharing the original grades given by the referees, but convince the public verifiers. Okay, so the for simplicity, we want to replace the grade given by the budget referee by X1, uh, grade by the risk referee by X2, and grade by ROI referee by X3. And if we replace these values, we'll see a simpler formula for the circuit. Okay. Now we want to go for the first step. We want to convert the puzzle into a standard circuit or design the constraint system. Okay, what is a constraint system? A constraint system is a system that asks you to design a scenario or a puzzle in a way that the proof system could understand and could read. So different proof system has different constraint system. So when the designer of a zero knowledge proof system, when they want to design a system, they define the constraint system. So the constraint system for Groth16 is a well-known system that is called R1CS. And R1CS says that each constraint should be written in a general form, term 1 multiplied by term 2 equals to term 3. And what is term 1 and term 2 and term 3? They are some affine combination of the variables. So the variables are the input or the intermediate values in the circuit. Now we want to see what is a R1CS constraint with some examples. So suppose that we want to see that if this one is a valid constraint system for Groth16 or not. Okay, so what is X1? So X1 again would be the input of a circuit, X1, X2, and this V1 are the intermediate values, right? For instance, maybe we consider the output of the first gate as V1, right? So in this circuit, V1 equals to X1 multiplied by X1, right? So suppose that we have another circuit which is like in this form. So x1, x2, x3, right? So x1 is multiplied by x2 minus x3, and we have a constant value like x5, like 5, and they are do some computation, and then the output is this term. So if we multiply these two terms to each other, the output equals to 1. And now we want to see that if this is a valid constraint in R1CS or not. So the general definition says that you can have two terms here, right? So this is term 3. So this is term 1, right? Which is multiplied by term 2, and this is term 3, right? So this is term 3, this is term 2, and this is term 1, and this is the multiplication between term 3 and term 1 and term 2, right? So the general formula is correct. Two terms are multiplied to each other and equals to term 3. Now we need to see that if each of term 1, term 2, and term 3 are affine combination of variables or not. So what is affine combination? So affine combination means that you can add the variables to each other. For instance, x1 plus x2 plus x3 blah blah, it is an affine. But x1 multiplied by x2, this is not an affine combination. So since the first term is affine combination, and the second term also affine combination, and the third one also affine combination, so then this is a valid constraint in R1CS. So this would be valid to be used by Groth16. So let's see the second example. So the second example, so this is term 1, this is term 2, and this is multiplication between term 1 and term 2, and this is term 3. So term 1 is affine combination of variables. Term 2 also is affine combination of variables, and term 3 also affine combination of variables. So then this is also a valid constraint. So the third example. So the third example says that I'm going to consider this one as term 1 and this one as term 2. Maybe you want to decide this one as term 1 and this one as term 2, right? So there is no difference. Okay, so let's consider this one as term 1, this one as term 2, and this is the multiplication between term 1 and term 2. And this is term 3, right? So the term 1 is a valid part because this is affine combination of variables. But the term 2 is not an affine combination of variables. So we already mentioned that multiplication between variables is not considered as affine. So since term 2 is not affine combination of variables, so then this one is not a valid constraint, right? So this means that if we want to design our circuit based on Groth16 or R1CS, we cannot have such a gate in our circuit or such a constraint in our constraint system, right? So for instance, let's consider this one. Consider this circuit, this gate, right? So this gate, what is architecture of this gate? Suppose that the output is V3. So this one, for instance, is V2. So the output is V3. So the gate V3 equals to X1 multiplied by X2 multiplied by X2, right? So we can consider this one as term 1, term 2, and term 3. And this is not a affine combination of variables. So this means that if you designed your circuit in this form, this is not a valid gate based on Groth16, right? So this means that this circuit, which is valid when you want to define your function or your puzzle, it is not valid when you want to define it for Groth16. You need to revise the circuit in a way that all the gates are valid based on this definition. Okay, so based on this discussion about the definition of R1CS, now we want to revise this circuit in a way that leads to a valid circuit uh, which is proper for Groth16. So, okay, so first we want to convert this formula or this puzzle into a valid circuit. So first we want to define this term, right? So we define V1 equals to X1 multiplied by X1. And we see that in our circuit as a multiplication gate. So this is a valid gate, right? Or this is a valid constraint. So this is the constraint, and this is the gate. So when we define our puzzle or scenario in a constraint system or in a valid circuit, they are equivalent to each other, right? So that's the reason we say that you can write the scenario either in a circuit form or in a constraint system. So the first constraint is this one, which is the valid, and that is generating the gate number 1. So the second part, we want to handle this term in our scenario. X1 multiply X, sorry, this term. Yeah, this term in our scenario. X1 multiplied by X2 equals to V2, and this is a valid gate or a valid constraint, right? So then we want to manage X2 multiplied by V2, right? Which is this one, right? X1 by V2, X2 multiplied by V2 would be this term in our scenario. So then we define the third gate or the third constraint, and they are valid based on the R1CS form. Now we want to define the final constraint, which is a big constraint, and we want to see that if this is a valid constraint or not. So if you have such a constraint, x2 would be the term 1, x3 is term 2, and this part is term 3, right? So this part is an affine combination of variables. So V1 is the output of the first gate, V2 is the output of the second gate, and V3 is the output of the gate number 3, and Y is the output of the whole circuit. So since the right part is an affine combination of variables, so this means that this is also a valid constant. and we want to design this constraint in a form of gate in our circuit. And now we have this addition gate that add all of these values, and this is a multiplication, right? So this is multiplication x2 multiplied by x3, right? I did not write multiplication here because if I write multiplication here, so then this could be counted as another gate. So then we would have 1, 2, 3, 4, 5 gate, but I didn't write multiplication here, so it will not consider as another gate. So now our circuit has just 4 gates. So maybe somebody define instead of this complex constraint, maybe somebody define two other constraints, right? Like x2 multiplied by x3 equals to v4, right? So this means that he has v4 here, then define the multiplication here, and then v4 equals to y minus 3 minus v1 minus v2 minus v3, okay? Something like that. And this is also a valid form if you want to define your puzzle. But the difference here, if you write in this form, you will have 4 constraints, or your circuit has 4 gates. And why? 5 constraints or 5 gates. So, and why 4 gates or 4 constraints is better than 5 gates? So later you will see that the more number of your gates in your circuit, the more complex your computation. So this means that if you want to write an efficient code or efficient circuit, it's better to try to hold the number of gates smaller. So that's the reason we trying to use this constraint instead of the other 2 constraints. Okay, so the first step is done. We convert the puzzle into a valid circuit or a list of constraint system. Okay, now we want to, so this is the valid, so this is the puzzle, right? So the puzzle converted into a valid circuit or a list of constraints. So these two are equivalent to each other, right? Okay, now we want to run the next step. So the next step is converting the constraint system into matrix. So when the prover enter the first values for the first company, you remember that the first value 1, 2, and 2, they are assigned by the referees for the first company. So the prover put the first value as the input of the circuit and then compute the output. And now prover need to generate a witness vector, which is shown by W. So this is the general formula of the witness vector. So the first term always is Y. The second term is the output of the circuit, Y. So then you have the list of inputs, X1, X2, and X3, and then you have the list of intermediate variables, Y1, Y2, and Y3 in this circuit, right? So this is the witness vector shown by W. So Uh, since the auction man or the prover here knows the value for x1, x2, x3, so then the prover can follow the circuit and compute the value of V1, V2, and V3, and then replace this part of the witness vector, right? So this is actually a knowledge that the prover or the auction man doesn't want to share with the public, right? Okay. So other than the witness vector or witness matrix, we need to define mm, the matrix of XL, and then the matrix of XR, and then the matrix of XO. So XL is the matrix related to the left inputs to the gates. XR is the matrix to the right inputs to the gates, and XO is the matrix related to the output of the gates. So we have four gates in our circuit, right? So that's the reason we have four rows in each matrix. So the first row is related to gate 1, the second row is related to gate 2, the third row is related to gate 3, and the fourth row is related to gate 4. Now we want to see how we fill this matrix X1, XR, and XL, XR, and XO. So let's focus on the first row in matrix XL. We mentioned that this is the left input uh, of the gate, and the first row is gate number 1. So this one, right? Okay, first let me erase this part. Okay, so let's focus on this row. So this row is related to the left input of gate 1. So in gate 1, right? So on the left input, on gate 1, there is no constant is as the left input, right? So that's the reason we put a 0 here for the constant. So, okay, so our matrix, we already mentioned that the number of rows is related to the number of gates, right? Number of column also is related to the element of the witness matrix. So the first element is related to the uh, constant value. The second element is related to the y value. The third is related to x1. The fourth related to x2, blah, blah, right? So now we see that we want to check the first row. The first row is the left input of gate 1. So what is the left input of the gate 1? So this is gate 1, right? And this is the left input. So the left input is given from x1, right? So that's the reason we put 1, which is related to x1 based on the witness vector on the first row, right? So other values would be 0 because there is no left input uh, from x2, there is no input from x3, there is no input from v1, there is no input from v2, and there is no left input from v3 for the in gate number 1, right? Okay, since we focused on gate number 1, let's check the first row in matrix XR, which is shown the right input in gate 1, right? We focused on gate 1 here. So what is the right input of gate 1? So the right input of gate 1 also again is X1, right? So that's the reason we will replace the position of X1 in here by 1, because the right input of the gate 1 is also X1. And other values would be 0, because there is no other right input in gate 1, right? Okay, so what about the output of the gate 1? So this is the matrix of uh, related to the output, and this is the output of gate 1. So the output of gate 1, we see that the output of gate 1 is V1, right? So that's the reason I'm going to replace the position of V1 by 1 to show that the output of gate 1 is 1. Okay, now you understood how we fill the first row of the 3 matrix. So you see that now our matrix is kind of describing the gates, right? The first row of the matrix are describing the uh, gate 1. So let's focus on gate 2 now. On gate 2, we want to first consider the left input. The left input of gate 2 is X1, right? So that's the reason I'm going to replace the value of X1 by 1 in matrix of L. The right input of gate 2 is X2, right? So then I'm going to replace the position of X2 by 1, right? The value number 4 is related to X2, and then I replace the position of X2, the value number 4 by 1. And what is the output of gate 2? It is V2, right? So that's the reason I'm going to replace the position of V2 in row number 2 of matrix X2 to show the output of gate 2, right? We will do the same thing for gate 3 and the same thing for gate 4. So gate 3 is easy, but let's overview gate 4 to ensure that you got the idea. Now we want to focus on gate 4, which is the uh, fourth row of the matrices, right? So first we want to check the left input of gate 4, right? So what is the left input of gate 4? So the so we want to follow the constraints, right? Because this is the definition of gate number 4. So if you look at the circuit, you may think that, oh, we have 4 inputs to the gate. So what is the left one and what is the right one? And then what about these 3? So no, we don't have 5 gates as input, 5 inputs to this gate. If you consider gate in this form, you will see that you have 1 input as left, 1 input as right, and this is the output. So since this is the real description of gate 4, based on this description, we see that the left input is X2. So that's the reason I'm going to replace the value of X2 by 1 in the matrix of XL, which is the left input of the gates. So the right input of the gate number 4 is x3, and that's the reason I'm going to replace the value of x3 in the rows number 4 of matrix XR. Now, this is the output. So the output of the uh, gate number 4, we have y. So that's the reason I'm going to replace the y by 1. Also, we have -3, and -3 is a constant value. So then I'm going to replace 1, which representing the constant value, by -3. And also we have minus V1 as the output. So then I'm going to replace the value of Y1, V1 by -1 and minus V2. So I'm going to replace V2 by -1 and also -1 for V3. So I will replace -1 for V3. So other values would be replaced by 0. Okay, done. We kind of convert the circuit or the constraint into the matrix, right? So this is the constraint. They are converted into the list of matrix. Okay, so now we have the scenario, the correct constraint or circuit, and also the list of matrix. So what is the proposed scenario now for the prover to convince the verifier? So now there is a naive protocol. So the naive protocol says that if the prover send the W, the witness vector, to the verifier can check such a test. The transposed vector of W multiplied by XL, which is the matrix of left input, and then multiplied by the XRW transform should be equal to XO, which is the matrix of output, multiplied by transform of the witness vector. So, okay, so this is the vector W known by the prover, right? The prover knows this W because the prover knows the input and also intermediate values for V, and then can replace these values. So then the prover send this vector to the verifier, and if you compute these values, if you multiply XL by WT, you will reach to this value. And also, then the verifier multiply XR by WT and then reach to this value. And then multiply these two values to each other, and this is the answer. And this is for the left side of the equation. So the right side verifier need to compute XO multiply WT, and this is the result for XO multiply WT, and we see that these two values are equal to each other, right? Since these two values are equal to each other, so verifier could convince. Now verifier is convinced that the prover really knows the x1, x2, x3, v1, v2, v3 associated to the value of y, which is 14. So this means that the prover knows all the input value and intermediate value for the circuit. Good. But the question here is that what is the concern What is the issue with this protocol? So the concern here is that the protocol is not succinct because suppose that the size of circuit is so big. For practical scenarios, we have so big circuits. So then we will have so big matrix, and the verifier needs to do the multiplication for so big matrix. And then this multiplication is expensive. It is not succinct, right? And also, if the if the size of circuit is so big, the size of uh, vector of W also is not small. So the size of proof also is so big. So the other concern is uh, ZK concern, which is actually more important for us. So if the prover sent W to the verifier, the prover actually shared the values for x1, x2, x3 with the verifier. But remember the original scenario. We want to design a scenario that prover could convince the verifier that I have followed the circuit without sharing the inputs. So that's the main concern of this naive protocol. Okay, now we want to go for the next step and address this concern. So the next step says that you need to convert matrices into polynomials. And we use the Lagrange interpolation algorithm. So this is the matrix XL. So we have a list of values for the first column, and we use it L sub X. And we have a list of values for the second column. And for the third column, and now we want to see, for example, how we compute those polynomials. For instance, for the third column, we have 1, 1, 0, 0. To convert this value into a polynomial, you remember that for polynomial, we need set of points, right? And for each point, we need x value and y value. So that's the reason we define points in this form. Point 1, point 2, point 3, and point 4. These are the values for the x. We consider these values for the x. And what are the output? We consider the first y as the first value in this column. We consider the second y as the second value in this column. So the third y would be 0 because the third element is 0 in the column, and the fourth y value equals to the fourth element in the column. Now we converted each column into a set of points, and since we have a set of points, we can convert the set of points into we can convert the set of points into a polynomial, right? Okay, what is the polynomial related to this set of points? We already compute the polynomial related to this set of points, right? If you remember, this was actually the list of points that we discussed at the beginning of this lecture. Okay, now we use the Lagrange interpolation and we convert this list of points or the column number 3 into this polynomial. And with the same scenario, we can convert the other column into polynomials. And you can use our website to check what are the polynomials for other columns. So now we define L of X, which is the matrix that's consider the coefficient of computed polynomials, right? So this is the polynomial related to the third column. So we replace the original value of the third column with the coefficient of the polynomials, right? We replace column number 3 with the coefficient values. And now these coefficient values are kind of describe the polynomial. So to rehearse, you can consider column number 4. You can convert this 4 value into 4 point and then use the website to ensure that if the Lagrange interpolation for column number 4 is this one or not. Okay, if you got the idea, now we can convert the other matrix into the matrix of the coefficient of the polynomial. So we will do the same thing for matrix XR and convert it into the matrix of Rx, which is the list of coefficient of the polynomials, and also XO into the matrix of XO. Okay, so now we have the matrix of the coefficient of the polynomials. Now the algorithm of Groth16 says that you need to convert this column to each other and reach to one specific polynomial. And that is enough for us. So instead of having a matrix for whole polynomials, we convert we combine these polynomials. So this was the polynomials L of X, right? And this was the polynomials L of 2, right? And this was the polynomial L of 3, right? So how we combine these polynomials to each other? We multiply the first polynomial with the first element of the witness vector. We multiply the second polynomial by the second element of the witness polynomials. And we also do the same thing for other polynomials. For the final polynomials, we multiply by the final element in the witness vector. Okay? After multiplying those polynomials to those values of the witness vector, we add the result to each other and we reach into one polynomial which we call it as L of X. So now this L of X is kind of a combination of all the left input of the different gates and the witness vector of the whole circuit, right? So you kind of combine those knowledge into just one polynomial. Okay, if we do the same thing, multiplying the 8 polynomial of R of X by the 8 elements of the witness vector and add them to each other, you will reach to R of X polynomial, which is representing the matrix of R of X, and also O of X, which is representing the matrix of O of X. Okay, now instead of working with matrix, we can work with polynomials. That's it. We kind of convert the circuit, the puzzle into a circuit, and then circuit into a matrix, and then matrix into polynomial. Now, prover wants to prove something on polynomials instead of matrix. Okay, so this was the naive protocol, right? It was designed based on the matrix. But now we have polynomials. How we can design a design mm, a proof system using the polynomials. So if you remember the previous lecture, when we discussed the polynomial, we discussed equality tests and pairing and all of those stuff. And using of those stuff, we designed a proof system. Okay, now the, the prover knows polynomial L of x, R of x, and O of x. So definitely prover doesn't want to share this polynomial to the verifier, right? Because these polynomials are kind of combination of the witness vector uh, and the matrix. And if somebody knows this polynomial can retrieve the witness vector. Okay, how we can design a test to ensure that prover knows this polynomial? Okay, now if we check, now we want to try to design a test. So like here, so when we had the matrix, we designed this test for the verifier, but now the prover knows polynomial, and we want to try to design a test for verifier. So let's see. Let's for instance assume that uh, this is the verification test for the verifier. So this will not be a correct test, right? Because L of x here is from degree 3, R of x is from degree 3. So L multiplied by R would be a polynomial of degree 6. And that would not be equal to polynomial O of x, right? So then this is not a correct and valid test for the verification. So what are other options? So this is actually a good contribution for Groth16, which is designing such a test. So the Groth16 says that first you define a target polynomial. The degree of target polynomial equals to the number of gates. We have 4 gates here, right? So since we have 4 gates here, we multiply x minus 1, x minus 2, x minus 3, and x minus 4, and we reach to this polynomial. So then Groth says that if you have t of x, L of x, R of x, and O of x, you can design such a test. And what is h of x? The t of x is a public values, public polynomial, because it is just multiplication of x minus 1 minus 2 blah blah until the number of gates. Everyone can compute this polynomial, right? So t of x is a public polynomial that if somebody knows the number of the gates, which is a public knowledge, then anyone can compute t of x. But L of x, O of x, and R of x, O of x, they are not public knowledge. So then, if the prover knows these polynomials L, R, and O, so knowing the polynomial T of x, the prover can compute polynomial H of x. How? Using this formula. H of x equals to L of x multiplied by R of x minus O of x over Q of x. So the prover who knows L, R, and O could replace this division and compute H of x, which is minus 1 over 18x to the power of 2, blah, 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 right? Okay, now prover knows L, R, O, and H, and T is public. So are these 5 polynomials is kind of uh, hints for you? So if you remember previous lecture, we discussed a concept given from these 5 polynomials, right? So yeah, this was the scenario of the previous lecture. If a polynomial like t of x is public, who knows L, R, O, and H that satisfy this equation, right? And this is actually the final test related to Groth16. So now the prover knows L, R, O, and H, and wants to convince the verifier that I know this four polynomial in a way that satisfies this equation. And if the prover could convince the verifier, then verifier would be convinced that the prover really knows these input values, right? So, so instead of working with matrix and sharing those matrix, now the prover just need to convince the verifier that I know those four polynomials. And based on our discussion in previous lecture, what was the solution for such an algorithm? Yeah, we needed a trusted authority to generate some SRS values, and then the prover needs to commit to the polynomials, and then share to the polynomials, share the commit values to the verifier, and the verifier compute pairing of the left and right equation. If the pairing are equal, then verifier convinced that the prover knows the knowledge. Okay, since these polynomials are actually the polynomials discussed in previous lecture, and also all of the setup protocol is the same, so the commit value are the same, and the verification test also is the same, right? So now you see that all of the discussion in previous lecture was actually the final part of Groth16 protocol. So let's review again how Groth16 works. So somebody who is a challenger or questionnaire design a puzzle, design a scenario. And the scenario in our example was this one. Then you need to convert the scenario into a valid circuit or a constraint system. Then you convert the circuit into a matrix. Then you convert the matrix into a polynomial. Now you need a trusted authority to generate public parameter SRS values. And prover now commits to the polynomials and send the commit value to the verifier. And the verifier run pairing and see the left and right side are equal and convince that the prover really knows these values, right? The prover really knows these input values. Okay, so if we want, so now we see that the prover actually is replaced by the auction man, right? And the verifier also is a public verifier. Why? Because everyone can run this pairing, right? Everyone who could use our website and compute this pairing value could be a verifier, right? The verifier doesn't need any secret value. That's the reason we have a public verifier here. Okay, so yeah, let's review the previous lecture very quickly to remember what was the scenario. Yeah, the previous protocol in previous lecture mentioned that who knows these four polynomials that satisfy this equation. We needed a trusted authority to generate these values, and then the prover convert these polynomials into mod n, and then commit to the values and send the commit values into for the verifier, and verifier run these parts, right? Okay, done. We convert the polynomial into a commit, and then the verification test is this one, right? So this is the verification test for this succinct as ZK protocol. Okay, now let's go back to our okay, now let's review our discussion in the first lecture. You remember in the first lecture, we discussed that there are two custom design and general purpose system, ZKP system, right? The custom design, like where is Waldo, and the color bulb and those ZKP systems. But later we mentioned that there are some general purpose system that you can manage all the puzzles, right? For instance, you can prove that you know the uh, correct answer of a Sudoku puzzle. And then we claim that we can use Groth16, right? Yeah, we finally did this because we designed a general purpose system, right? You can define any puzzle into a constraint system, right? So for instance, if you want to work with Sudoku puzzle, you you convert your Sudoku puzzle into a correct circuit or correct constraint system, right? Then the prover converts the circuit into matrix and then generates the polynomial, and then a trusted authority generates SRS. Then the prover generates the commit related to the polynomials and send to the public. Then public verify the pairing and ensure that the answer is correct, right? So this is a general purpose. The only responsibility now is to convert the puzzle into a constraint system, into a circuit. So this is our responsibility after this. So whatever puzzle that you have, you just need to convert the puzzle into a valid constraint system, which is defined based on R1CS. And then after that, Groth16 system would manage everything, right? That's it. Okay, now we want to discuss another concept. So we already mentioned that we have designed a general purpose ZKP system by Groth, and it could manage all the scenarios, all the puzzles. So let's discuss another thing. What happens if we have another different circuit, which is given from another scenario, but the circuit is different, right? So this is the circuit related to this formula, right? But this is a circuit related to another formula, right? So this might be another project or another contract that evaluate the final grade of the application based on another formula. So that's the reason we have another circuit for this scenario. So if we do the same steps related to this circuit, so then what happened? We will reach again to this step, right? So we'll finally say that what is the four polynomial that satisfy this equation when the uh, when the public polynomial T of x is the same for this circuit, right? Okay, so now we have four different circuits related to four different puzzles, but the T of x related to these polynomials are the same. So this means that if a prover knows four polynomial, right, four polynomial related to the fresh circuit, the prover can use those four polynomial and claim that I know the correct polynomial related to the other circuit also, right? Because everything that bind the circuit number 2 is polynomial T of x. So this means that the knowledge L, R, O, and H related to the first circuit can satisfy the second circuit, right? And this is the concern of soundness. How we can guarantee that the four polynomials are actually related to that specific circuit, following that specific architecture for that circuit. So let's discuss the puzzle in previous lecture again. In previous lecture, the puzzle was this. Uh, a polynomial like T of X is public. Who knows four polynomials L, R, O, and H that satisfy this equation? So the puzzle just asked the prover to prove that he knows four polynomials that satisfy this equation. This puzzle could have billions of answers, right? You can design so many polynomials that answer and satisfy this equation. So that's the issue. So prover could convince the verifier that I know four polynomials, but the problem here is that the prover could not convince the verifier that these polynomials really follow the circuit. I really knows the input. I really compute different gates of the circuit and then convert the intermediate values into the matrix and then convert the matrix into the polynomials. And these four polynomials that I have are actually the polynomials that are given by from following the circuit and knowing the original input of the circuit. So this is the soundness concern. So now we want to make the protocol uh, better to answer this concern. Okay, so what is the general idea? So the general idea is that we want to kind of uh, uh, okay, so we want to kind of make the trusted responsibility of trusted authority in a way that the SRS value are kind of given from the architecture of the circuit, right? We kind of uh, give a knowledge from the architecture of the circuit into the public parameter. Okay, let's see how. So yeah, the first version of the test was this one, right? We discussed that this is not enough. This is not enough. We want to revise this test. Okay, so the protocol says that the trusted authority needs to choose two random value, alpha and beta. And like tau, these two value also should not be shared uh, by the trusted authority. Okay, so after uh, considering these two values, let's see how the verification algorithm is changed. So we want to work on this uh, equation. We want to add L of x by alpha and add R of x by beta. And then we want to multiply these two terms to each other. You have this one. Okay. Now we replace this part from this formula. So we have L of x multiplied by R of x replaced by O of x plus T of x multiplied by H of x. Now, if you remember from previous lecture, we mentioned that the prover doesn't need to send all of the polynomials to the verifier. Prover just computes the evaluation of the polynomial at point tau, right, to the verifier, right? So the first test was this one, and the first test is converted into this one. And verifier, the prover wants to convince the verifier that I can satisfy you that I know the knowledge related to this equation. Okay, then we discussed in previous lecture that the evaluation at point tau is not enough. The prover needs to compute some commits. and to compute some commits, we discussed that we multiply the value by G1 and then convert this equation into pairing of G1 and G2, and then using the properties of pairing, we change the formula in this form. Okay. Okay, now we have this formula instead of the first test. So what are these formula? So the commit of the first polynomial, we discussed in previous lecture how we compute the commit of polynomial L of x, right? It would be an element in group G1, right? You remember. So what is alpha G1? Alpha G1 also a value that is computed and shared by the trusted authority, right? The trusted authority knows G1 and knows alpha, so the trusted authority multiply G1 by alpha, and you can use our website to ensure that the value alpha G1 is computed correctly. So this is public parameter. So after the prover computes commit of L of x based on the steps discussed in previous lecture, you just need to add this element by alpha G1, and that is just addition of 2 points in group G1. Again, you can use our website to compute this part. So then the commit of polynomial R of x is an element from G2, prover computed based on our discussion in previous lecture, and then added by the value beta G2. And the beta G2 also a public value that is computed by the trusted authority by multiplying beta at the value of G2. Using our website, you can check to ensure that this value is correct. And then the prover can add the elements of group R2, G2, and these elements of group G2 using our website again, addition of 2 elements in group G2 to compute this part. For the right side, we have these values, R of tau, L of tau, O of tau, and then if we consider the vector witness, we can replace these values by public parameters. So the psi1 equals to G1 multiplied by alpha R1 tau plus beta L1 tau plus O1 tau. So from here, alpha multiply R plus beta multiply L plus O of tau. So using these values, if the trusted authority generates these values based on the definition that we discussed about how to compute commit of a polynomial, you may, if you want, you may review the concept how to compute a commit of a polynomial from previous lecture. And then using those discussion, the prover can compute commit of h of tau and also multiply these values, W, the witness vector, into psi values. So the psi values are computed by the SRS, by the trusted authority and shared as SRS. And these W's, they are the secret, right? The secret that the prover knows, and then can multiply these values to the psi values and then send those values to the verifier. Okay, so let's see what happened here. You remember that the at the verification side, when we discuss the naive protocol, we need to multiply W by L, R, O, and those matrices, right? So now we kind of multiply the element of the vector into the commit of the polynomial R, L, and O. And so the commit value, to compute the commit values, the trusted authority generate these psi values. The psi values are needed for the prover to kind of compute the commit of polynomials. And then the prover needs also the knowledge of W, the vector of W, to compute the multiplication of the witness to the commit of the polynomials, right? Okay, now we have this test. So instead of test version 1, the prover sends these values and these values and these values to the verifier, and verifier will check this test. And if this test is valid, so verifier is convinced that prover knows the knowledge. So let's compute this test. So test version 2 says that prover needs to compute commit of L plus alpha G1. Commit of L computed in previous lecture, right? You know that it was a point in group G1. Alpha G1 is computed by the trusted authority. So commit of G1 is an element in group G1, and alpha G1 is an element in group G1. So now we have 2 points in group G1, and we want to use the point addition tools in our website. And if you do that, you can see that you can bring the commit of L from previous lecture and then add it by this value in our website, and you will see that this part would be 4 and 28. For the next part of proof, a prover needs to compute commit of R plus beta G2. Commit of R computed in previous lecture, right? Beta G2 committed in SRS, the public parameter. So you will add these two values, bring the commit of R from the previous lecture and add it by this value in our website, and you will see that this is the final result of the two elements. So then the prover needs to compute this part. So commit of T1 is this one computed already, and commit of W1 multiplied by psi1. So W1 is 1, W2 is 14, W3 is 1, blah, blah. And so W1 psi1 equals to 1 multiplied 5571, right? So this is the value of psi1. So W2 equals to 14 multiplied by 27 and 78, which is psi2. So how we can compute 14 multiply 27 and 78? Yeah, using our website. So you can use the scalar multiplication part in our website and compute these values. So after you compute all of these multiplications, you will have 4 points in group G1, right? And then you can use a point addition tool in our website again to add those 8 points to each other, and you will reach to this value as the other parts of the proof, right? So 48 and 85 is this part, right? So this part also is computed by the prover. So the other part commits of t is 48 and 16. So now we need to add these two parts to each other. Again, you can use the point addition from our website, and you will see that addition of these 2 points equals to infinity, right? So this part, the whole part equals to infinity. Okay, now these parts are computed and add and sent as the proof to the verifier. The verifier needs to compute pairing of these two values and pairing of the other values to ensure that if all the computation is correct or not. So let me erase this. Okay, so the first part is computing pairing for the left side. So these two values are computed by verifier, by prover, and sent to the verifier. So this is the first part, and this is the second part. You can use our website again, the pairing, and if you use our website, you will see that the pairing of these two values equals to 5 plus 61i, right? So this is the left part of the uh, test version 2. So the right side, right? So for the right side, verifier needs to compute two pairing. So the first pairing is pairing alpha G1 and beta G2. So the value of alpha G1 is computed by the trusted authority, and the value of beta G2 also is computed by the trusted authority, right? So verifier get those two values from the public parameters and uh, compute the pairing. You can use our website and compute the pairing of these two elements, and you will see that this is the result of this pair, right? For the other part, this part is shared by the computed and shared by the prover. So the value equals infinity, right? And G2 also is part of a public parameter, right? So G2 is in public parameter. So verifier take the G2 from public parameter and infinity as the proof from the uh, prover, and then compute the pairing of these two values. You can use our website, and you will see that the pairing of these two elements equals to 1. And 1 multiply 61i plus 5 equals to 61i plus 5, right? So you see that these two values are equal to each other, right? So the left side and the right side are equal to each other, and then the verifier is convinced that the prover is the prover really knows the knowledge, and also the prover follow the circuit, right? Because the test version 2 is kind of consider the property, the architecture of the circuit, like R, L, and O. They are polynomial that kind of describe the architecture of the circuit, right? So the architecture of the circuit now is part of a public parameter, and the prover generate the proof based on those uh, public parameters which are bind to the architecture of the circuit. So that's the reason now we convinced that prover knows a knowledge that really uh, computed based on following that specific circuit, not any other circuit, but with the same number of gates, right? So test number 2 now is addressing the concern of uh, uh, soundness, and this is good. Okay, now we want to discuss that test version 2 is not enough, you know. So test number 2, version 2 is better than test version number 1, but still test version 2 is vulnerable by some attacks. So Uh, you remember that this was the witness vector, right? So we can see that if the prover replace the witness vector with another witness vector by adding as an extra zero here, right? So the prover just add an extra zero. We need a space here between y and x1. So if the prover add an extra zero here between 1 and y, so the prover again could convince the verifier that I know the correct answer. I know the witness victim. So, and this is not good because uh, in some scenario, the prover can share its knowledge like W with another uh, malicious prover, and the other malicious prover can generate W prime and then pass test version 2 and claim that I know another different circuit, another different secret, right? So suppose that we have a secret, we have a circuit that uh, needs to know different kind of knowledge. So the first knowledge is W and known by the prover, and it passing test version 2. So the prover can share this secret with another malicious prover, and he can add an extra zero as past test version 2 and claim that I know another secret for this circuit. Now we want to address this issue. So uh, we see that the witness vector consists of two parts, the public part and the private part. Public part consists of the public values. Everyone knows one and everyone knows the y because the output of the circuit is shared by the public, right? By the value of x and v, they are the secret value that prover doesn't want to share it with public, right? So if we write the public and private vector of W prime, we see that the form of public and private would be different from the valid uh, public and private part of the witness vector. Okay, this was the test number 2, right? We want to uh, consider the public part and the private part, and then disjoint from two parts from each other. You remember, based on the properties of pairing, you can have these two parts disjoint from each other, right? So this part is W1, W2 until WL, which is the final element of the public values of the witness vector. So here we have two elements. So then we have W1 and W2 here as the public values. And these are the are the private values. So here we see that L equals to 2 for our scenario. So W3, which is X1, is the first element of the private, and this is the other private element of the witness vector, and this is the last private element of the witness vector. So we kind of disjoint the public and private value in our vector, in our witness vector. Okay, now the trusted authority again needs to consider two random values, gamma and delta. Definitely will not share it with with public, with others. And now we want to multiply the gamma here and 1 over gamma here. So based on the property of pairing, you know that we can add these two values here, right? Because based on the property, you know that you can bring 1 over gamma to here and multiply by gamma, and then gamma multiplied by 1 over gamma equals to 1, and they can remove, right? So that's the reason we can add gamma here, and also we can add a delta here, and also 1 over delta to remove the effect of the added delta, right? So then you bring 1 over delta to here, 1 over gamma to here, and 1 over gamma, 1 over delta to here, and then uh, instead of psi 1, the trusted authority needs to compute psi 1 public, which is actually 1 over gamma multiplied by psi 1. So psi 1 is already computed in previous test version 2. So if psi 1 divided by 1 over gamma, so psi 1 public would be computed, right? So then 1 over this value, so this value was psi 1, right? 1 over gamma multiplied by psi 1 equals to psi 1 pop. Psi 2 pop also computed by the trusted authority. So this means that these values are already computed by uh, trusted authority. And I'm going to give you a hint to see how we address the discussed concern. So here we see that the system is trying to disjoint public and private uh, values, right? Public and private element of the witness vector. And then the SRS for the public are computed by a different element from the SRS for the private. So the private SRS are divided by 1 over delta, and the uh, SRS for the public are divided by 1 over gamma, right? And that's the reason if if a malicious prover put a 0 here and then bring y here, the neo value would not be past the test version 3. So that's kind of prevents the malicious prover to kind of add an extra 0 before y. Okay, now test version 3 is based on this formula. The prover needs to compute these values, and then these values, and then these values, and then these values, and send them to the verifier, and verifier will check this test, and if it passed, so verifier is convinced. Okay, so let's see. So the new SRS value also computed. So similar to previous discussion, you can check using our website all of these SRS values to ensure that they are computed correctly. Okay, test version 3 says that the commit of L plus alpha G1 computed in test version 2 already. The next one also computed in test version 2. Now the prover needs to compute these values, right? So these values, omega W1 multiplied by psi1 pop plus W2 psi2 pop. So W1 equals this one, right? And this is 14 for this one. And psi2 pop is given from the SRS values, right? And then again, we have a list of multiplication, a scalar multiplication, and then addition of different points to each other. And this is the final result for this computation for this part, right? So we have the commit of H. It is computed already. No, this is not computed already because it should be divided by G1 over delta. So again, we have these values. And finally, we reach to these values as the other proof. Okay, as I said, we need all of this. We can do all of this computation using our website. Okay, when the prover compute this value, he will send this value to the verifier. The verifier will check and compute the pairing for the left side, which is computed this one, and then the pairing of these two values that are given in the SRS and multiplied by pairing of these values. Again, we see that the results are equal to each other. So you can use our website and check to ensure that the pairing of these two values equals to this value, and the pairing of these two values equals to this value, and then the multiplication of in the extension field, you can also check this multiplication to ensure that this computation is correct. Okay, test version 3 is better than test version 2 and better than test version 1, and it is passed by the prover, right? This is good. Everything is done? No. So test version 3 also is not enough. And let's see why this is not enough. Okay, so now we want to discuss another concept. So suppose that we already mentioned that we are designing a general purpose system, right? So suppose that our circuit is a circuit like related to the age verification, right? Suppose that we design a circuit that somebody needs to enter their birthday, and then the circuit do some computation and finally compute the age of the user, right? So based on our current architecture test version 3, a prover can enter the birthday as the input of the circuit, and then the final proof would be shared by the verifier. Verifier would be convinced that prover really follow the circuit and do the computation correctly, and also prover doesn't add any zero before y, and the test version 3 is against previous concept. However, suppose that there are two provers that they have the same. So then, what happens to the proof? What is your guess? So we have a circuit that computes the age of a user based on the input. So if two users has the same birthday, they enter the same value as the input of the circuit, so then the output would be the same, and the intermediate value of the circuit would be the same. So the polynomial would be the same, and then the commit would be the same, and then the proof would be the same, right? So now we have two users that are sharing proof, and the proof is exactly the same. And then the user number one could distinguish that the birthday of the other user is the same to his birthday. And similarly, user number two can also distinguish that the birthday is the same. And this is kind of uh, concern of zero knowledge, right? So you don't want to uh, allow somebody to distinguish your birthday when, uh, when you are sharing the two copies, right? So we have another scenario that can show the uh, concern of privacy. Right? So this is that you see that finally the prover just shared the value, the output value 14, and the proof to the verifier, right? So the the system claimed that uh, zero knowledge is guaranteed, but somebody may try to guess the input, right? You can you can try and put 0, 1, 1 for x1, x2, x3, or other value, and check random value and follow the figure. And finally, you see that for one set of value x1, x2, and x3, the output is 14, right? In this scenario, also, the the verifier can guess the input. Okay, now this show that the test version 3 also is not enough, and it should be updated to uh, solve this concern. Okay, let's see how we solve this concern. The ZK concern. Okay, so to address this concern, the prover needs to choose two random value R and S, right? So different from the previous values, tau, alpha, beta, gamma, delta, that are picked by the trusted authority, this R and S should be picked uh, by the prover. So then using this property related to the pairing that we already had, so we can convert we can add uh, R delta gamma here and S delta gamma here at the left side, right? Using the property of the uh, pairing, we will have on the right side this one. So based on this property, we will have these values on the right side. Now we convert the right side into this form. So for instance, we remove our delta from here and put it on as the power. For the other elements, yeah, for this, the element number 2 and number 3, yeah, they are combined to each other to reach this element. And the first element, it doesn't change, right? The first element, it doesn't change. Okay, now we have the left side and the right side. This part is not changed. The right side, we remove S from here and we bring S into here. This is a property that we can do in pairing, right? So for the third one, we don't have any change. So now the first one, doesn't change, the second doesn't change, and for the third one, delta comes here and R comes here. Again, this is the property of for pairing, right? Pairing of P and Q to the power of N1 and 2 equals to pairing of N1 P and N2 Q. Okay, now this is the final version of the test. Yeah, here you let me see. Yeah, here. So here we have pairing of commit L plus alpha G1 and pairing R plus beta G2. From test number 3, we replace this one by these 3 terms, right? By these 3 terms. And then we have these 2. So then we say that the pairing of the left side equals to the pairing of the right side of test number 3 plus the extra part of the right side. So this one, this 2 1, and then also the these 2 values also should be combined by this part of the pairing in test number 3. Okay, now this is the test version 4. So now the prover, the trusted authority also needs to share beta G1 and delta G1 because we need them in the new test. Delta G2 here, sorry, delta G1 here is needed, and beta G1, yeah, here, beta G1 also needed by verify. So these 2 values are computed by the trusted authority, and then this is the test version 4. So the prover will send these new values as the proof, and verifier will check. So let's compute to see that if the test is passed or not. So beta G1 and delta G1 are computed by the trusted authority and shared in SRS or public parameters. So the test version 4 is this one. So we assume that prover pick 12 and 13 as random. So definitely prover doesn't want to share these values to public, right? And then the commit of L plus G1 already computed in test version 3. So that was an element in group G1. So the prover knows the value of R, and also the delta G1 is a public values, right? So first the prover multiply R by the delta G1, the result would be an element in group G1. Then add the value of R delta G1 by the previous value that computed in test version 3. And if you compute those values, you will see that this is the final result. So again, the prover knows the value delta G2, yeah, here, delta G2 from public parameters, and also S is randomly computed, it randomly pick 13, and then 13 multiplied by this value. You can check it using the website, and then add with this term that computed in test version 3, and using the website, you can ensure that this is the final values. So now the left side is done. For the right side also, the prover do all of this multiplication and then addition of the values using the uh, SRS and using our website. So if you check our website, you finally reach these values and you will ensure that all of these computation are correct. Okay, prover send these values to the verifier and verifier compute pairing of these two elements. Use our website and you will ensure that the pairing of these two elements equals to 51i plus 13. And the pairing of the right side also, you can check the pairing of these values, and these values to ensure the pairing are computed correctly, and then multiply the values using the multiplication tool in the extension field, and then you see that the pairing of the right side also equals to each other. Done. So these two values are equal to each other, and then the test is passed. Now test version 4 is completely secure. So the issues in test version 1, test version 2, and test version 3 is solved, and test version 4 is the final test. So now you can be happy that you got the idea of the Groth16. Okay, so let's review what happened. We described a scenario, and then a prover uh, needs to prove that I know the input or the secret grade uh, assigned by the referees as the input of the circuit. I follow the circuit, so this is the output of the circuit for the first company, and this is the proof. So this proof actually consists of all of those values, right? In previous, let's go back to the previous website. Yeah. So all of these value, this value, these values that should be sent to the verifier, they are called pi. So the prover needs a trusted authority to generate those SRS value, and test version 4 is the only test that need to be checked, right? The only test and the valid test. So prover consider the first element for the first company and share 14 and the proof to the verifier, and verifier can run this test to ensure that the first uh, computation for company 1 is correct. Again, prover put these three values as the input. 3 here, and then 1 here, and then 3 here, right? And then follow the circuit, and then the final computation is 21. So prover needs to compute the polynomials again, and then compute the commits, and then pick R, S, and then finally generate this new pi for 21 for the second company. For the third company, the same things would be sent to the public, and then the public could run this test version 3 for this one to ensure that the first computation one correct. So again, test version 4 for this one, test version 4 for this one, and finally, the public could convince that all of the computation was correct, and prover convinced the public that the final grade are computed correctly and nobody cheated. And then the public could convince that the contract was fair, right? This is good. And now we finally reach to a general purpose system that you can use for any kind of puzzle. You can convert the Sudoku puzzle into a circuit, and then anyone who claimed that I know the correct answer could enter the correct answer as the input of the circuit, and then generates the matrix and then polynomials, and then commits to the polynomials to generate the mm, commit values and proof. And finally, a public verifier can run test version 4 to convince that the knowledge was correct. Okay, uh, I'm happy that we finally finished this complex concept related to Groth16. If you got the whole idea in this series of lecture, now you finally got the idea of Groth16. In next lecture, we will see the real computation and real implementation of Groth16 with real and valid values for prime. So prime is considered 101 in our computation to make everything easy to understand. But next lecture, you will see the implementation with real value for prime. Thank you and see you in next lecture.